Welcome to this lesson on temperature and gas. Today, we're going to explore one of the most fundamental concepts in chemistry and physics, the relationship between temperature and kinetic energy. Understanding this connection will help you grasp why gases behave the way they do and forms the foundation for studying gas laws. Let's start with a crucial question. What exactly is temperature? Temperature is a measure of the average kinetic energy of particles in a substance. In simpler terms, it tells us how fast molecules are moving on average. When you feel something hot, the molecules in that substance are moving very quickly. When something feels cold, the molecules are moving much more slowly. Temperature isn't just a number on a thermometer, it's directly related to the motion of tiny particles we cannot see. Now, let's talk about kinetic energy. The kinetic energy formula is Ke equals 1/2 mv squared, where m represents the mass of a molecule and v represents the velocity or speed of that molecule. This equation shows us that kinetic energy depends on two things: how heavy the molecule is and how fast it's moving. The faster a molecule moves, the more kinetic energy it has. This is important because in gases, molecules are constantly in motion, and this motion directly relates to temperature. Here's the key concept. There is a direct relationship between temperature and molecular motion. Higher temperature means faster molecular motion. Think of it this way. When you heat a gas, you're adding energy to it, which makes the molecules move faster. When you cool a gas, you're removing energy, which slows the molecules down. This relationship is proportional, meaning if you double the absolute temperature, you double the average kinetic energy of the molecules. This is why temperature is such an important property when studying gases. We can express this relationship mathematically. The average kinetic energy equals 3/2 times K times T here. K is the Boltzmann constant, which is a very small number that relates energy to temperature, and T is the absolute temperature measured in Kelvin. This equation is powerful because it shows that average kinetic energy is directly proportional to temperature. If you know the temperature, you can calculate the average kinetic energy of gas molecules, and vice versa. You might wonder why we always use Kelvin for gas calculations. The answer is simple but important. Kelvin starts at absolute zero, which is the point where molecular motion stops completely. At 0 Kelvin, molecules have no kinetic energy at all. This makes Kelvin the natural scale for gas calculations because it directly relates to molecular motion. Celsius and Fahrenheit have arbitrary 0 points that don't correspond to any physical meaning. But Kelvin's 0 point is absolute, making it perfect for scientific calculations. Let's look at the practical implications of this relationship. When you heat a gas, the molecules move faster and collide more frequently with each other and with the walls of their container. This is why heated gases expand and create more pressure. On the other hand, when you cool a gas, the molecules slow down and collide less often. This is why gases contract and exert less pressure when cooled. Understanding this helps explain everyday phenomena, from why hot air balloons rise to how refrigerators work. Let's summarize what we've learned today. First, temperature measures the average kinetic energy of molecules. Second, higher temperature means faster molecular motion. This is a direct, proportional relationship. And third, always use the Kelvin scale for gas calculations because it starts at absolute zero, the point of no molecular motion. These three concepts form the foundation for understanding how gases behave and will be essential as we continue exploring gas laws in future lessons.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.